So there we are. Okay, go ahead. The Zoom chat is available to you as well. And chime in. We're 18 strong, so we can be nice and civil. All right, so let's continue on with chapter 5. And so as if you've seen the videos, we again go in a different order here. Now I want to focus just on carbocations, the nature of the carbocations and things that they do. Okay, so we need stability, possibility of rearrangements, and then the fact that they act the way they react to form final products, okay? So the first thing is that our carbocation is a positively charged carbon, okay? It has 3 bonds that are all sp2 hybridized, and it only has a total of 6 electrons, meaning it has a formal charge of +1, okay? So the bonds that, the sigma bonds it forms are those sp3 hybridized, and that makes them trigonal planar. So they're nice and flat, and that means that unhybridized orbital is sticking above and below that plane. We're going to use that in chapter 7 to decide how things are adding to our system. So the idea that that orbital, that p orbital is above and below that trigonal planar, those 3 sigma bonds, is important, okay? So because we have a positive charge actually on carbon, they are electrophiles, okay? So because they are electrophiles, that also means they're Lewis acids. They're willing to accept an electron pair, okay? So electrophile and Lewis acid are synonymous. Sometimes I'll use electrophile, sometimes I'll use Lewis acid, but they are the same thing, okay? So let's look at that trigonal planar structure here. The more stable a carbocation is how many other electron donating carbons it'll have. But the idea that the next step in the reaction after you form this, you can either have something attack this part of the positive charge or this part of the positive charge, will become very important in chapter 7. So we just need to recognize that that exists and that it'll direct where our properties are in our future reactions, okay? So our tertiary carbocations are the most stable carbocations we form. If at all possible, things will rearrange to make that happen, okay? So our tertiaries form fastest because they have the lowest activation energy. Our secondaries are sometimes hard to do, but when they do it, they can rearrange, so we have to think about that. Primaries and the methyls are very difficult to make. They are very rarely observed in solution, if at all. Usually you have to do it in some kind of vapor phase laser kind of work, okay, because they're not very stable. So the most important thing we have to think of is secondary and tertiary carbocations are the primary ones we have, with tertiary being the most stable, and it'll rearrange to form that most stable part, okay? How do we recognize that we have a carbocation? By just looking at the energy diagram. Okay, remember the carbocation is observable and occasionally isolatable, so that means it's an intermediate. It's a reactive intermediate here, okay? And now that it's looking for electrons, it is an electrophile. It has a lower activation energy when that carbocation reacts with other things. So that means forming the carbocation is the slow step, okay? The carbocation is the intermediate, and forming it is the slow step. Once it reacts, then you just have the interaction between a nucleophile and electrophile, and that reaction happens very quickly, okay? So that means we're looking at 2 parts. Carbocations participate in pattern 3 and in pattern 4, okay? The reaction between an electrophile and a nucleophile to form that covalent charge. In this case, our positive charge is the electrophile, okay, or the carbocation. The nucleophile is something with electrons. It's going to form that new covalent bond, okay? So if we're thinking about this as whenever we form that, the first step happens and that first step happens in pattern 5. But once we form that carbocation, it reacts typically in pattern 3, that nucleophile electrophile motion. Okay, so again, it'll also happen in pattern 4 because it'll rearrange to try to make the most stable carbocation possible. So this is most of the time going from a secondary carbocation to a tertiary carbocation. You will never go the other way, but it'll always be a secondary to a tertiary by either moving a methyl group or a hydrogen. Those are the only two things that are going to rearrange to do that. Okay. And a methylene, so a CH2 bonded to something else, if it's in a ring. But if it's in a straight chain, it's a methyl CH3 group or hydrogen. Okay, so the other pattern that we recognize in carbocation is what we call pattern 5, where we break the bond to form a stable molecular ion. Again, this typically happens only to make tertiary carbocations because the tertiary carbocation is the most stable ion that can be formed on carbon. Okay, so once we form this, it is now the reactive species and can happen. So carbocations happen in pattern 3, 4, and 5. Okay, so because of the stability of the carbocation here, that directs why we cannot make this primary alcohol from this reaction. And the thing happens because if we added the hydrogen here, we would have a primary carbocation. Never form a primary carbocation. You'll never see that product in any substantial amount. So because if we added the hydrogen to that side, we would get this primary carbocation. We don't form this. If we added the hydrogen to the opposite side, and I'm going to add the hydrogen over here in blue, if we add we'll end up with a secondary carbocation. Okay, and notice that if we did a 1,2 methyl shift here, we would only get a secondary carbocation. So if we tried to move this methyl group over, we would still have a secondary carbocation. Therefore, this product will not undergo pattern 4. It will not undergo a rearrangement because it would go from a secondary to a secondary. Okay, so we don't have to worry about that happening in this particular case. Okay, let's look at this again. Okay, in this case here, we do see pattern number 4, rearrangement. But again, when we add our hydrogen, to our side here, because that gives us our secondary carbocation, we have the opportunity of moving a hydrogen. Oh, wait, hold it. We don't have a hydrogen next to there. So we have the sigma bond to a CH3 group. So we can move this over one carbon. That's why we call it a 1,2 carbon shift, because we're moving from one carbon to the carbon next to it. So it's a 1,2 shift to create a more stable tertiary carbocation at this center here. So this is the tertiary carbocation. This is a secondary carbocation. So let's say, why do we have 2 products here, okay? If the tertiary is more stable, okay, but it has to form the secondary first, okay? And once it forms the secondary, it can react as the electrophile. But while it's waiting around for those electrons to come to it to make that new sigma bond, it has an opportunity to rearrange to the tertiary. So when we do form some of this product, that means that we had it reacted before it had a chance to rearrange, okay? That's why we have a product distribution and not just one product. We had a carbocation, it reacted before it had time to rearrange. So this is formed by taking that first addition and doing pattern number 3, nucleophile electrophile. This actually went on to do pattern number 4 and then did the addition with the electrophile and the nucleophile. So that's why we have a product distribution and not just one product. Okay, so actually, there we go. All right, so again, that first one was the shift of a methyl group, a 1,2 shift moving that methyl group. You can also have it happen by just moving a hydrogen. And in this case here, what we're doing is we're moving a hydrogen for it to go from a secondary to a tertiary carbocation. So what I'm going to do is I'm actually going to redraw this species here, right here on the next slide, and then I'm going to show you how that hydrogen transfers over. But again, it does it the same with a methyl group or not. So we have this, redraw the compound here. We have a CH3 group here. We have a CH3 group here. We have a hydrogen here. We have our bond here. We have our double bond, and it has a hydrogen on it. And I'm going to draw the hydrogens here so we can see where they move. Okay. How do we know when there will be a product distribution or just one product? Okay. Anytime that you form a secondary carbocation and it can rearrange, you typically have at least some of it react to give you that secondary carbocation. However, the major product will be the tertiary carbocation. So anytime you can create that secondary, you will have a product distribution. But again, in all product distributions, the more stable intermediate gives you the primary product. Okay, so let's look at that, what can happen here on this too. I'm going to apply your question to this problem as well. So the first step in our reaction here, and let's just add HBr. And so the first thing we're going to do here is I'm going to change colors of ink here, because these electrons here are going to reach out and grab that hydrogen to create our new sigma bond. The electrons that were here are going to go onto the bromine. So our first step is just that reaction, and that's going to give us CH3, CH3, hydrogen, 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 and our new hydrogen here, plus our bromine negative charge. Okay, because it's got 4 lone pairs on it now. So we're going to keep that in our pocket. That's going to be our nucleophile we're going to react with later. But we're just doing this. We've now created our carbocation here, and that's our secondary carbocation. Okay, we have 1 carbon attached to it, 1 carbon attached to it, and 1 hydrogen attached to it. So 2 carbons, 1 hydrogen, secondary carbocation. Okay, so that's the first step here. Now, if this compound reacted immediately, maybe this bromine didn't drift away very fast. Okay, so maybe it's really concentrated and it has an opportunity to react this bromine before it has a chance to diffuse away. Okay, that would control product distribution, saying that, oh, if I had a really good solvent and the bromine just kind of dissolved away in the solvent, we have time for it to rearrange to give us that tertiary carbocation. If that solvent wasn't a very good solvent and that bromine didn't go very far, then it would react and we get the reaction with the secondary carbocation. So in blue ink here, I'm going to draw the product of where this secondary carbocation is going to react with this bromine here and give us one product. And this time I'm not going to draw the hydrogens so that we can get used to skeletal structure right here. And that secondary carbocation is going to give us just our bromine here and our methyl group at the end. Okay, so again, I went back to skeletal structure so that we'll keep in our minds where the hydrogens are. But we didn't have a hydride shift. We just had that secondary carbocation react because that bromine did not drift away. Okay, let's say that bromine kind of shifts over here, gets far enough away that we can't feel it electronically, and now we want to shift something. Okay, so now we're going to shift. I'm going to change colors again here, and we're going to do pattern 4, our shift here. We have options here. We have a moving of a methyl group or a moving of a hydrogen. Okay, now whenever possible, it prefers to move a hydrogen because the hydrogen has less mass. Okay, so if we had 3 methyl groups here, it would move a methyl group. If we have 2 methyl groups and a hydrogen, it will always move the hydrogen because the hydrogen has less mass. So if we move these electrons over here, That means all of these electrons are going to make that new sigma bond. We're going to come up with our new product of hydrogen is here now. We have our hydrogen here and our 3 hydrogens here. And now we have a CH3 and a CH3 and our carbocation. We now have our tertiary carbocation. Okay. Again, hydrogen shifts faster because it's lighter. If you can move a hydrogen, always move the hydrogen first. If you have to move an alpha group, that's the next thing that's going to happen. And then, of course, when this reacts, I'm running out of colors of ink, so I'm going to do it in black here. When this reacts with the bromine, we're going to end up with our other product. Bromine is on that tertiary carbocation, and the hydrogen is moved over to the other system. Okay, so this is the product from our tertiary carbocation, and this is the product from our secondary carbocation. Boy, that doesn't look like a 3, does it? Tertiary. Okay, so that's how the shift works. That's why the shift works, and that's why we see both products. Because if this reacts as the secondary, because of concentration or solvent, we will see that product. Okay, does that answer your question, I think? Okay, let's move on to the next slide so you can get all the way through here. Okay, now, when we do carbocation rearrangements in the presence of rings, that's when things get really confusing, okay? Now, the thing we have to think about is when we have rings, the smaller the ring is, anything less than 5 carbons is strained. It wants to pop open, okay? And anything greater than 6 actually has too much floppiness. So the 2 rings that organic materials like to form are 5-membered rings and 6-membered rings. And so if you have an opportunity to make a 5-membered ring or a 6-membered ring, it will happen. And that's what we see in these cyclic carbocation rearrangements. We're not just moving a CH3 group, we're moving a CH group that's attached to something else. But the driving force for this is the idea that, ooh, I get to go from a strained 4-membered ring to a less strained 5-membered ring. And ooh, I get to go from a 5-membered ring to a 6-membered ring. And so that's why the carbocation rearrangements in rings happens. And that's the driving force. We're still forming a more stable carbocation. In the case of this compound here, we're actually going from a tertiary carbocation to a tertiary carbocation, but we're opening up a 5-membered ring into a 6-membered ring, and that gives it less strain, okay? So this is kind of one of the tricky ones to see sometimes, but if you look at the starting material and look at the product, you'll say, oh, it must have undergone a 1,2 methylene shift, a 1,2 carbon shift, such that you can create that less strained ring. And that's what to look for in this particular pattern. So I would say this is number 4 pattern with a caveat of expanding a ring to make it less strained. Okay. I have extra slides there somewhere. All right, so the net goal of chapter 5, goal 2, is that the carbon has the positive charge. It's sp2 hybridized, meaning it's trigonal planar. Tertiary is more stable, secondary is next most stable. We almost never form primaries. Okay, so all our products are going to be derived from a secondary or tertiary. If you can move a methyl group or a hydrogen over, you're going to get to this 1,2 group shift to get to the most stable. You will only do it if you're getting to a more stable carbocation or releasing strain in a ring, okay? Carbocations are stabilized because it can pull electron density away from those neighboring carbons. So if you have 3 carbons bonded to that carbocation, it is the most stable. 2, a little more, but if you only have that 1 carbon or no carbons at all, it's very difficult to stabilize that positive charge. I think I have one more. There we go. The last one. Okay. So Once you form a carbocation, it does three things. It can either rearrange and give you a 1-2 shift to give you a more stable carbocation, and then react some other way. Or it can react with a nucleophile to form that new carbon-carbon bond. So if you already have a tertiary, it's probably just going to react with a nucleophile to create that new covalent bond. The last thing it can do is actually going to lose a proton to give back the alkene. Now, we don't see that product when we look at our reactions because that turns it back into the starting material. Okay, so we don't see it happening, but there's probably a significant amount of the things starts to come up the reaction curve. It forms the carbocation, but instead of going through to the products, it actually just gains that hydrogen back. Okay, or I'm sorry, loses that proton to give you back your alkene. So while this last one, we don't actually talk about it, it does happen, but it doesn't give us products. Okay, the rearrangement gives us two products. The addition of the nucleophile gives us the product we're looking for, but that step 3 gives us our starting material, so we don't typically see it. Okay, so that's goal number 2, chapter 5. And any questions on that? I can move on to goal 3 of chapter 5. Okay, in goal 3 of chapter 5, I'm going to talk about the reactions. And what I want you to start recognizing is that those 5 patterns appear in all of these reactions. Those 5 patterns appear, and it also drives whether or not our products are what we call syn addition, where we're adding something to the same side, or anti-addition, meaning it starts on one side and the other one comes on the other side. Okay, now, if you form a carbocation, then you really don't know which side it added on because you can add it on to either side. So look for those 3 things as we look at these different reactions independently. Okay, so we have the reactions in this set. We have the hydrohalogenation, or adding acid across the double bond. We have hydration, adding water across the double bond. We have halogenation, adding a halogen onto both carbons of the double bond. Okay. We have hydroboration, which seems to go backwards, but when we look at the polarity of the hydrogen-boron bond, we see it goes on exactly the way it should from the perspective of nucleophile, electrophile. And then our last reaction is our hydrogenation. Remember that our halogenation is an anti-addition because of its intermediate. Our reduction in our hydroboration are syn addition because it's reacting on the one side of the reaction. And when we go through carbocation, it can be either. We don't know which side the nucleophile attacked on because we have sigma bonds, and those sigma bonds have free rotation. Okay, so let's go and look at the electrophilic addition of the alkenes. Again, with the hydrogen halides, we're going to add the hydrogen to the side with more hydrogens because of the stability of the carbocation. In water, the OH will always appear on the more substituted carbon because of the stability of the carbocation. And in the halogenation, we have one halogen wind up on each side of that carbocation. And again, each side of that double bond. And we don't have the rearrangement because our intermediate forms that 3-membered ring, that bromonium ion or the chloronium ion, which is that 3-membered ring. So we see anti-addition because of that formation of the ring, and we don't see rearrangements because we don't form a carbocation. So let's look at those independently, okay? So again, our addition of halogen, acids across that double bond, give us the hydrogen on the more substituted side. It's a regioselective reaction, and it follows Markovnikov's rule. Markovnikov's rule is an observation of the stability of a carbocation. The more stable the carbocation, that's where the halogen is going to end up in the addition of hydrogen halides or acid halides. Okay, so we're following the rules on that one. The same thing happens in water, except instead of having a halide end up on your carbon, you have an OH end up on your carbon. Okay, so instead of adding think of it as a proton and a chlorine across the double bond. You're ending a proton and an OH. So it's almost identical, except we have a different starting material. And because of that, it's following Markovnikov's rule again, because it forms a carbocation, and therefore the non-hydrogen group, in this case OH, winds up on the more stable carbocation. So that means in the hydrogen halide reaction and the water reaction, we follow Markovnikov's rule, and we can have carbocation rearrangements. Okay. So I want to take a moment here and look at this. This is the addition of an alcohol to an alkene. It follows the same mechanism as the addition of water, but I want to go stepwise, because what we want to see is that this alcohol here is basically analogous to water, because in the case of water, we have this structure here, and the only thing we've done is take one of these hydrogens away and turn it into a carbon. So while the mechanism's the same, the product is different. We actually end up forming an ether, and we'll learn a little bit more about that in chapter 8, but we're forming a different functional group. So I wanted to take a little time to look at the mechanism and the product here. Again, so what we're doing here is we are going to do the exact same thing as we do in the acid catalyzed addition of water here. We're going to end up protonating the alkene here to give us our carbocation. And when we do that, we have CH3, CH3. We have a carbocation here, plus this is the two hydrogens that were on there to begin with. And then I'm going to add this hydrogen here is the one from the acid catalyst here. Okay, so the first thing that has to happen is step number 1, proton transfer. We add a proton to it to give us this carbocation. Okay, so now that we have our carbocation, we now have an electrophile. Okay, it has a positive charge, it's looking for electrons. Okay, in this case, what's going to provide the electrons is, again, the lone pairs on the oxygen of the alcohol. Okay, so these electrons are going to come in and form a new sigma bond here, giving us our intermediate. And let's see if I can draw our intermediate here. C, methyl group, and methyl group. See how this has become a methyl group here because we've added those hydrogens there? So this is a CH3, a CH3, CH3. And then we have our new bond with our oxygen here, which now has the positive charge on it because 2 of this lone pair turned into that new sigma bond. So we have a hydrogen, another lone pair, and the CH3 group here. Okay, so we're not done. We've done the pattern 3, the reaction with the nucleophile and the electrophile. But we need to do one more step to get us to a neutral species, and that's give the proton back. We're going to give this proton back to more methanol, this CH3OH. These lone pairs on the regular methanol can take that proton back, giving us our neutral species, which is our product, our ether. Okay, we followed all the rules. And the same rules we have for adding water across there, but instead of making the alcohol, we've made the ether. Okay, so I'm glad we ran through that entire mechanism showing you where the new bonds are forming and breaking. Okay, so now let's look at the addition of the chlorine and a bromine across it, okay? When we do this, we actually ran an experiment. They ran an experiment with the cyclohexene to prove that it was anti, okay? Now, in a straight chain alkene, you might think it would be difficult to understand that it's anti, that it adds opposite each other, because it makes a sigma bond, and that sigma bond has free rotation. And so that, you know, you can just say, well, it just twisted, you know, that it could have added on either side. But when we do it with this, we lose that ability to twist around that sigma bond. And so it tells us that we had to add the second bromine opposite to where the other bromine was to give us that anti-product. So this is the proof that it is anti, even though we don't quite see it in a straight chain. And so that's, I think, the importance of using cyclohexenes in some of our reactions to help us probe the mechanism, okay? Now notice, when we do this, it actually ends up, we form the bromonium cation on the top, and then the other one has to come from the other side to give us this. So when it first reacts, this is the bromine that was on the top right here. This is the one that came in. And so they're anti to each other. They have to be opposite. But as we know, having the largest groups in those axial positions is not the most stable way to have on a cyclohexane. So it's going to go ahead and flip till it has the two big groups in its equatorial positions. And so those bromines are still trans to each other because of the way they added. However, we just showed the more stable conformer of how the cyclohexane flips back and forth. So while these are the exact same products, they are the anti-addition products right here, we actually can draw it in these two different configurations, knowing that this one is more stable. Okay, so actually, yeah, okay, good. All right, so now let's look at the hydroboration experiment. And again, we figured out that it was a syn addition when we did it in a cycloalkene, okay? When you do it in a cycloalkene, the hydrogen and the boron add to the same side of the double bond, okay? So that means it's a, number one, stereo selective reaction, meaning that we know that they had to add across the double bond at the same time. And we know it's regioselective because the hydrogen actually carries the positive, partially negative charge, and the boron carries the partially positive charge, leading to its seemingly anti-Markovnikov's addition, okay? So that's the really important part about the hydroboration. It seems to go backwards. The hydrogen is adding to the less substituted side, and the boron's adding to the more substituted side, but it's because of the bond polarity and this intermediate formed right here. That four-membered transition state where the hydrogen is adding and the boron is adding at the exact same time. That exact same time gives us syn addition, same side addition, and therefore we can prove this by using the cyclohexenes. Okay. Now, the next reaction is a reaction between the hydrogen adsorbed to the surface of the metal and an alkene. And because we have that surface, and because we've done this reactions on hexene, we see that we can actually, cyclohexene, this is actually a syn addition. We have to have that double bond come sit flat on the surface and both hydrogens are added to the same side. Okay. Now, remember, this is, if you look at the mechanism, this is actually the pattern number 3, electrophile nucleophile right here, where the alkene is the electrophile and the hydrogen polarized bond on the surface of the metal is the electrophile. Okay, so in one of our last reactions here, we have the reaction of the acetylene, okay? And the first thing we learned about acetylene is because of that sp3 hybridization, having so much S character, it can handle a negative charge better than other carbons, making it more acidic. Now, this is also the first time we've done a reaction where we made a carbon-carbon bond. And the way we do that is we take that proton off the acetylene to make it an anion. Once we have that anion now, it is now a nucleophile. It is looking for something that it has a partially positive charge. And in the case of this substrate, it turns out it's that polarized bond between the carbon and the bromine, where bromine is more electronegative, and so it's taking away electron density. So this is the partially positive side of the bond. This is the partially negative side of the bond. And now our anion is attacking this partially positive carbon to kick these electrons out with the boron to give us our product. So In this case here, it's pattern number 3, nucleophile electrophile attack. And just because we reacted one side of the acetylene doesn't mean the other side's any less reactive. We can still deprotonate that and do it again. So again, in the synthesis, we're using pattern number 3, but we're also the first time we're making carbon-carbon bonds. So we can actually expand these out again and again. All right, I have some reactions I want to get to at the end here. So, but if you have questions, please go ahead and ping them in here. Okay, so a triple bond is just 2 pi bonds, right? So they react exactly the same way an alkene would in the catalytic hydrogenation. So it'll reduce it all the way down to the alkane unless we make the catalyst less reactive. And that's what we do when we call it Lindlar's catalyst. We call it making it less reactive by adding these lead salts. So if you think Lindlar catalyst, think lead salt, think less reactive. If it's less reactive, we can stop at the alkene, stop at the double bond. So we only are taking one of the pi bonds down, the other pi bond stays, giving us the alkene. Notice this is that syn addition, so that'll always give us our cis alkene. Both of the hydrogens are added on the same side of the double bond, giving us our cis alkene, our syn addition, same side addition. Lindlar, lead, lower reactivity, cis, syn addition. Okay. All right. So now let's do some reactions right here for the next few minutes here. And what I want to do is, starting with acetylene and any other necessary reagent, we're going to propose a synthesis for these compounds. And once we've made a compound, we can use it again in another reaction, okay? So I want to start thinking about all those different patterns we've seen and those reactions we have and carbocations we might form. We're going to use all those to actually do synthesis on our next couple slides here. All right, so go ahead and ping any questions as we go, or chirp in if you have an issue here. So the first thing when we start attacking a synthesis problem is we want to make butane from acetylene. Okay, so whenever we attack a problem like this, let's draw the product so we know where we want to go with it. Butane, so that's 4 carbons with a triple bond, and the triple bond is on the end. So that means our product is going to look like, let's see, that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, and we have a hydrogen at the end here. I'm not going to draw any of the hydrogens. We're gonna imagine they're there. Okay, so we're looking at skeletal structures only. So if this is the product we want to form, and we have to start with acetylene right here, we just did that reaction, right? So what we're going to do is we're going to take the acidic hydrogen off the acetylene, turn it into a nucleophile, and react it with something. So that means our first step is going to react it with sodium amide. Sodium amide right here. Right here, this is one of those really strong bases. It's got a negative charge on nitrogen, which makes it really, really basic. So it's going to pull that off. It's going to create our acetylene anion right here. And okay, so now we have a nucleophile. So now we need to find something to displace. And so if this is our negative charge, in the previous reaction, what we showed was when we have a bromine on an alkane, this is a polarized bond. So we can use this to displace that and create our product. So that means we had to have sodium amide in our first step, and our second step is just a ethyl bromide, and that'll create our product right here. Okay, so that's how we attack problems. That's how I attack problems. I draw the product, I figure out what changed, and I figure out how to make that change happen. Okay, so our next thing we need to make is 1-butene, and the fact that we can use products we already made means we can use this as our starting material for the second step. Okay, so we have a triple bond, which is our butane. We want to go to our double bond. We only have one way to do that. okay? If we used catalytic hydrogenation, just regular catalytic hydrogenation, that'll take it all the way down to butane. So we probably don't want to do that. So that makes us think, less reactive, Lindlar's catalyst, lead. So what we do is we take our product we just made right here, react it with Lindlar's catalyst, with hydrogen, and we get our double bond right here, which is our 1 butene, okay? So we've taken what we know and we've converted it on, okay? So now that we've made that product, we can go to the next one. Now that we have the 1 butene right here, let's make 2 butanol and 1 butanol. All right, so gosh, we have an alkene. We just need to add water across that bond, right? So if we took this and added water and an acid catalyst right here, SO4 right here, which of these two products would we make? Would we make the 1 butanol or would we make the 2 butanol? Type. Okay, let's figure it out by drawing the first step in the mechanism, which would be the addition of a hydrogen, okay? So if we just added a hydrogen and used Markovnikov's rule, that means our structure would look like this. We've added our acidic hydrogen and we have a carbocation here, okay? If we have that carbocation react with water, that's gonna give us one product, okay, right? That product is gonna be our reaction with OH ends up on our product here, okay? So if we just did our standard addition of water, acid catalyzed on that alkene, we would end up with product number D here, product letter D. That would give our 2 butanol. But we cannot get our 1 butanol from this, okay? We have to go break the rules. We have to go anti-Markovnikovs to get to that 1 butanol. So the way we do that is, instead of forming this carbocation with the acid catalyst here, we have to use a different catalyst. I mean, we have to use a different reactant. So if instead we used the borane reagent first, and then we oxidized it off using some kind of oxidizing agent here, the first part of the product would be a hydrogen here and a boron with 2 hydrogens here. That would be the first step in that reaction. And then we'd have to oxidize it down. And when it oxidizes, it actually takes off the boron here and gives us our OH and, with on the end where the boron was, and gives us all of our 4 carbons in the rest of the chain. Okay, so if we want to make the 1 butanol, we have to use boron with oxidation. If we make the 2 butanol, we can just rely on the fact that it makes the more stable carbocation and gives us this product here. Okay? So I'm hoping you see that when you attack the problem, draw the product first and figure out exactly how you can get there. If the first step is forming this carbocation, you know you can't get to the primary alcohol. You have to get, you can only get to a secondary or tertiary alcohol if you form that carbocation. So you might have to use a different reagent, okay? So let's go to the next thing. So now we need to make 3-hexyne. Gosh, 3-hexyne. Well, let's start by drawing the product here. So let's figure out how we can get there. 3-hexyne. So hexyne, that's 6 carbons. And we have the double bond at the 3 carbons. So we have carbon, triple bond, carbon. And then we have 1 and then 2 carbons here. So this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6 here. So that's the product we're trying to make, okay? And we can use a reagent we've already made. So if we go over here, we already made 1-butyne using this reagent here. So we already made 1-butyne and it already has 1 CH2 on the side. So we can do this reaction again to the other side using this material to make the triple bond be in the middle of that chain. Okay, so let's figure out how to do that. So if we want that, and we can, hey, let's make it using the butane we've already made here. So if we start with butane, see, we'd have to react it with sodium amide again to deprotonate it, and then react it with a ethyl bromide, and that would give us this product here. Okay, what if we wanted to start with acetylene? Well, then we just do the same reaction, but we do it twice. If we wanted to start with acetylene, sorry, somehow shifted pages here. If we wanted to start it with acetylene, right here, we could then do sodium amide, followed by ethyl bromide, Br, CH2, CH3, that's ethyl bromide, will give us the first reactant to give us, again, the butane, and then react it again with sodium amide in the bromoethyl group here to give us our second one. And so both of the acidic hydrogens on acetylene have been removed, made into anions, used as nucleophiles to displace bromine to create that new carbon-carbon bond. And then, of course, to make the next product here, let's, of course, draw the next product. We have to make cis-3-hexene. So that means we have a double bond in the middle. And we have 1, 2, 3 carbons, because it's on the 3 carbon here. But it's cis. That means that that other thing has to be on the same side. Ooh. Let's see, that's 4, that's 5, that's 6. So we have the right number of carbons. So that means we just have to reduce this down using Lindlar's catalyst, because we know Lindlar's catalyst has lead salts and it adds sin, and it's less reactive. So we can get to this compound here just by reacting this product with Lindlar's catalyst here. Okay? So now that we have this sin-3-hexene, let's take that sin-3-hexene and turn it into these two compounds. Okay, so if we had the sin-3-hexene right here, to turn it into hexane, all we need to do is catalytic reduction of hydrogen with palladium, platinum, or nickel. And then it'll turn it into hexane because it'll reduce down that double bond. Now, if we wanted to get to the hexanol, we would just do water and acid. Now, why can we use just the water and acid for this one right here? Because it doesn't matter which side the hydrogen adds to, we're going to get a secondary carbocation. And so that secondary carbocation is not going to move because there's no way to make a tertiary carbocation. So that means the hydrogen is going to go on one side and the OH is going to go on the other, giving us our final product, 1, 2, 3, 4, 5, 6 of 3 hexanol. This is carbon 1, carbon 2, carbon 3. Now notice it can add the hydrogen to this side and it'll add it to this side, and it just changes which side we count on. If we add the hydrogen to this side, it'll add the OH to that side, and we'll end up with this product. So we can actually go nice, being a nice symmetrical molecule, we'll get to that nice one product from that reaction. All right, any questions on this? Okay, so We're using a strategy of drawing the product, trying to figure out what we have to do to make it happen, remembering that carbocations can rearrange, so we need to keep track of where things might have gone. All right, so now instead of making an alcohol, we want to make 3,4-dibromohexane. Okay, so let's draw our product here. I'm gonna draw it in green here. Bromo, bromo, and this is the 3, so that means there's 1. This is the 4, so that's 1, 2. So gosh, that looks like the addition of bromine across a double bond, which means our starting material, if we're gonna go backwards, is gonna have to be something like this. Now, why don't we have an alkyne here? Why couldn't we use the alkyne? Well, we could use the alkyne, except when we had the alkyne, we'd have to add HBr across it once and then HBr across it again, because we end up with hydrogens. We have 2 hydrogens here. So if we just took the alkyne that we made already and added bromine to it, the first bromination would give us a bromine across each one, which would give us a dibromo compound, but we'd still have an alkene. We don't have an alkene. We have an ane here, so it's saturated. So we can't just add bromine across an alkyne. So that means we need to add a bromine across this alkene. And we've already made that cisalkene when we took our alkyne and reduced it down, so that all we have to do is add bromine to that. It'll add 1 to the one side, 1 to the other, giving us our 3,4-dibromohexane. Okay, and that's the attacking the goals, using our reactions that we know, predicting from our mechanism which products are going to be the major ones based on the more stable carbocation. And again, whenever we do synthesis problems, it's great to draw the product and look at the reactions you have, and the reagents you have available. And between those 3 things, comparing and contrasting, you should be able to develop a good synthesis from each of these systems. Okay. Any questions on that? Okay, what I'm going to do is I'm going to stop recording here, because this is our 3rd one of goal, and then we can actually discuss. We are right at 1:45. I'm sorry I ran a little over. I will try to keep a better track of time.